You're originally from Moscow?
Yeah.
I was there. I was there years ago. You want both of us to look at you, or? I was there a few years ago. Goran Shlotikov invited me. Very interesting. We looked at Quantum Center, and
I was there.
you were there. So I was the first time walking around Moscow on my own. They didn't know English. Never were eating unpaid. Next morning was closed. See, pain and fever and lots of guilt. It was standing on the podium, shaking, really shaking all the time, getting ready to run to the toilet. That was my colloquium in Moscow. Yes. You know, everywhere, China, wherever, people are already used. Their stomach used from young age. Yeah, you never. Well, there was a lot.
We still have a few minutes before starting the section. So let me start making some announcements so we don't need to remove time for the most interesting part of the conference, right? First, if you're going to seminar 7 today, we changed the rooms. But the room is the one in front of the last one. It's exactly the same. But the thing is, the one that the seminar 7 is the one that has all the equipment for live broadcast. And today we have a little event of the federal government program CIS-Photon. And about 20 people are there, but they are broadcasting because many people are participating. And instead of moving all the instruments, we decide to... You're not even going to realize you move the room. It's exactly the same room, just in front. Okay? And we're going to have an indication where you should go. Seminar 7. The rest of it stays in whatever was originally. The second announcement is that today we have pizza. So after finish, you go there. We're going to have pizza and a special drink. No alcohol is allowed, but some fermented and tea is permitted. So you're going to have. What? No name drink. So please come and enjoy. So we're trying to promote more conversation, right? So please come and enjoy. You can have a few pieces of. The guy will be cooking the pizza there. So you're going to get a fresh pizza. And then you, after eating, talking, you can, probably you're not going to need another dinner. Maybe some people. Vlad, are you okay with pizza today? Okay, thank you. Okay, good. And tomorrow, before that, we are now organizing some trips to take you back to the airport. You see, we are doing this. Originally, we thought that putting a big bus on the airport will work. But I think you realize that your arrival is scattered along the day. So having 1 or 2 buses did not work. Some of you will have to wait for half a day in the airport. So the operation to pick you up, we put many vans. And we brought most of the people. Only a few got lost. And then they took an Uber. Now we are organizing the return. And we took all the part time that you provided to us, the ones that provide. And today we start with one vehicle that's going to take only 3 persons. I think you are included, Sid. And every time we're going to leave from here because the operation to go around the pick people is too complicated. I want to ask your cooperation to bring your bag here. If you are a little far, Uber costs less than $1 to come where you are here. And then everything departs from here in front of this building. Tomorrow we have also van and cars and so on. We're going to provide the transportation for the ones that already requested until the 10th, until the day after the conference. There are a big collection of people that's going to leave on the 13th, on the 14th. We cannot hold the operation until that time. So we are providing transportation until the day after the conference in the morning, okay? And but if you stay until the 13th, 14th, you are welcome. We can give you the instruction. It's very easy. We have buses here that stop on the bus station in São Paulo, and then a taxi in 20 minutes put you in the airport. And we will give you the instruction. Now, the important thing is, if you request help in returning, you should go to the desk of where you got the registration and check your name to see what time your vehicle is departing. Unfortunately, we cannot put one each hour, so some of you are going to have to wait a few hours in São Paulo. But we recommend you to do that. This weekend is a long holiday because Tuesday is a holiday. People connect with Monday, so the traffic in São Paulo this weekend will be a little heavy. So we are anticipating a little bit. It's better to sit down in the airport, relax, have a coffee. If you are fed of coffee, have a Guaraná or anything else, waiting for your flight, okay? Please go there and check what time your name is assigned. If you want to change, let us know. But you have to go there. Otherwise, we assume that you know, even though you have to go there to check. Finally, tomorrow we have many people is going to go for some tourism, some adventures. But you have to be back no later than 5 o'clock. Because then you have a time to go to your hotel, maybe take a shower or relax for a few minutes, because the dinner starts at 7. And again, many people gave it the name to get transportation from here to the restaurant where we're going to have the dinner. In that case, you should be here by 6:30. So you're the first to arrive, the first to get your drink, gloof, gloof, sit in a nice table until we fill it up the restaurant. Another day I said that you are welcome to take whoever is a companion person for you. But and then some students came to me, oh, can I invite my friend? The companion persons are the one registered. Okay? We set a dinner with a finite number. We cannot have more than 300 people. So, a companion person is like the wife of Zheltikov. If you brought your wife? So you go alone. Okay. But some people brought their wives, so those are the ones you can take. When I say take your companion person, doesn't mean go invite somebody in the street and go. We're going to require this for you because students already. Oh, can I take my friend? He is lives with me. No, you can't. What? If the girlfriend is registered and have this, you can take it. We are taking the number of people that register, right? So sorry, we would like to provide a dinner for the whole São Carlos city, but like in your case. And husband too. Yeah, okay, yeah. Of course, it's a symmetric problem. You can take your husband, no problem. Good point. That's a good point, Christian. Okay, so I think now we can start the plenary sections in the morning. And during the coffee, please go and check your name if you are leaving tomorrow or today or after tomorrow and so on. See in what vehicle you are located so we can. And a final thing is, of course, we cannot cover everything with the registration money. So I'm asking some of you to sign because we got money from other sources, but we have to prove that we use the money. And not all the money can be used for restaurant and things. It's like paying you for food. So please, if the secretary call you to sign it, what you sign is that. We want to make sure that whoever gave you the money is sure that we apply the money with the right people, okay? Okay, so I think that was the end of the communication. Now I pass the word to the chair of the section that will go on with this. Thank you.
Thank you very much. Good morning, everyone. I'll be chairing this session, this morning session. So our first speaker is Alexei Zheltikov from Texas A&M, and he will be talking about nonlinear optics of stochastic fields. Are we broadcasting? We are. Please.
Can you hear me back there? Thank you. Right, so I would like to start by thanking, of course, Wanderlei Bagnato for putting so much work, so much effort, and let me say so much heart and soul into what is happening here. So thank you very much, Wanderlei. This is a great job. You are our hero. And I would like also to say thank you to Olga Kucherovskaya. Olga, if you're watching, thank you for inviting me to give a talk here and for helping me, in fact, to reconnect with the laser physics workshop. Thank you, Olga, once again. So let's see, nonlinear optics of stochastic fields. And I have a privilege of being a speaker for a collaboration, so I'm speaking on behalf of and in collaboration with my colleagues at Texas A&M, Alexei Sokolov, Marlon Scully, Girish Agarwal, Zhenhuan Yi, and Gary Eden, who is also with the University of Illinois. And we'll also be using results of some experiments and computations that have been done over the years by our group here and there in different places at Texas A&M, at Moscow State University, at the Russian Quantum Center. So I will be using the results of our experiments and simulation as I will go over this talk. So to get started, I decided to put this slide together, optimists and realists' views of nonlinear optics, to have this introduction, to have a sense of where we are going with our notion of stochastic nonlinear optics. So first of all, the optimistic view, the way we usually introduce nonlinear optics is, nonlinear optics is to get new frequencies, broader bandwidths, no limits, shorter pulse widths, again, no limits, high radiance, high field intensities, supercontinuum generation, high order harmonics, high field physics, again, no bandwidth limits, sub-cycle field waveforms, parametric amplification, wonderful talk by Konstantin yesterday. Kerlen's mode locking, enabling technology, nonlinear polarization, another enabling technology for fiber lasers, optical soliton fiber communication, laser filaments with a plus sinus, meaning the positive side of laser filaments, attosecond pulses, and then the list goes on and on. But there's also a realist's view of nonlinear optics, right? It's on the right-hand side. Now I can view basically the same phenomena, the same nonlinearities as a source of problems, giving rise to spatial and temporal instabilities. Spatial, so my pulse becomes unstable, my beam tends to break up into filaments. So now laser filaments here, right? Laser filaments here are with a minus sign, right? So my beam breaks up into multiple filaments, and this is not what I want to achieve. Now my high order harmonics are a source of signal distortion, right? So I cannot deliver my waveform in a distortion-free way any longer. And then my physically intuitive Fourier space, my Fourier transform is no longer linear any longer, right? And I will get back to this point a little bit later, because of course it's a plus and minus sign to this. We can sort things out. So, and then from these optimists and realists' views of optical nonlinearities, I kind of decided that it would be meaningful to have the explanation in terms of several dichotomies of stochastic nonlinear optics. So it will be optimists versus realists' views of optical nonlinearities, and there will be deterministic versus stochastic aspects of field evolution. And I will talk about what is avoidable versus unavoidable in beam instabilities and pulse instabilities, and then classical and quantum in nonlinear wave instabilities. And then again, linear versus nonlinear Fourier space as a way to identify our normal modes, and in the end, to do field quantization. Right? So, of course, as we think about nonlinear optics as a source of problems, as a source of limitations, right? Of course, nonlinearity always sets a fundamental limit to the stability of nonlinear system. Right? It's general. Nonlinear optics, not necessarily optics, not necessarily even electrodynamics. Nonlinearity sets fundamental limits to the stability. And of course, in optics, this has been understood a long time ago. People started talking about self-trapped filaments of light back in the 60s, in the early days of the laser era. Then again, new class of trapped light filaments, phase modulation on Q-switch laser beams and small-scale filaments, and then fundamental theoretical milestone, dynamic formation of small-scale filaments. This famous Marburger paper with Marburger's formula of self-focusing. And then, of course, this 1965 early experiment on multiple filamentation by Filipetsky and Rustamov, where, in fact, multiple filamentation has been observed for the first time, 1965. Then this Palov-Talanov theory, another theoretical milestone, again talking about light beams in filamentary structure of light beams on nonlinear liquids, setting the framework for the theoretical description, something that we view as a gold standard of theory of nonlinear dynamics up until this day. Now, as a word of caution, of course, this is not what we understand as laser filamentation in modern terms. Right? In modern terms, we tend to think in terms of femtosecond dynamics, femtosecond laser pulses, and then usually ionization, ultra-fast ionization, as a part of this process is a very important ingredient of the process, something that makes this filament build up. This was not the case in earlier work. Of course, in the earlier work, filamentation was understood as in a more general sense, not necessarily involving ionization. And of course, the groups working toward laser fusion have been thinking and have been concerned with those beam instabilities due to induced by optical nonlinearities for a long time. So this is one of the early papers, and this is already a review paper in the Journal of Fusion Energy from Lawrence Livermore National Laboratory, discussing in great length this filamentation, once again, beam filamentation at high laser peak powers, and again discussing the gain as a function of the energy in megajoules. So the typical orders of magnitudes were all there, right, 43 years ago. Megajoules here along the x-axis, and then the gain, this break even is somewhere here when we start having more energy from the nuclear reaction than we are depositing energy from the laser beam. And of course, this story has a very important, very significant continuation these days because of the break-even achieved at the Livermore laboratory recently, which of course initiated several projects, and we are, Texas A&M is a proud member of one of the teams working as a hub funded by DOE. So our acronym is RISE. In fact, RISE is an abbreviation with all those letters picked up in a random order from inertial, R, we're taking R from inertial, I from fusion, S from science, and E from technology. And then this is how we are ending up with this nice acronym RISE. RISE Hub. And the goal is to advance laser-driven inertial fusion energy technology towards the readiness for future IFE, and again, inertial fusion energy demonstration. So it includes universities and then private enterprises, including Marvel Fusion in Germany, Exemer Energy here in Colorado, General Atomics, and then also national laboratories, of course, most importantly. And the vision of the hub is that the quickest path to the IFE is based on current technologies to develop high energy in excess of 10 megajoule lasers with direct drive targets. Now, as we tend to think about the major roadblocks and challenges along this path, we start thinking about that high energy laser beams combining based on neutral gas nonlinear optics, and nonlinear optics is needed here. Then nonlinear optics is also needed for high energy laser pulse compression. Then also we need to avoid laser beam instabilities, right? As we deliver high power laser beams, high energy laser beams, we need to avoid laser plasma instabilities already at the laser plasma interaction stage. And we need to avoid, again, wherever possible and whenever possible, laser target interaction instabilities. Right? So nonlinear optics it holds all the keys to confront all those challenges and hopefully remove those major roadblocks wherever possible. But some work needs to be done, and this is the mission of Texas A&M as a part of this consortium. So as we start thinking about stochastic aspects of nonlinear optics, right, when the fields are becoming complex and not necessarily deterministic, and we need to describe their evolution, their dynamics in an adequate way, of course, we also have some important history. Right? The group in Harvard published one of the earliest papers on the theory of Stock pulses in transit stimulated Raman scattering. So this is a milestone paper, heavily cited. Again, of course, the group in Moscow, Akhmanov, Dyakov, and Pavlov, had one of these very impactful publications, statistical phenomena in Raman scattering stimulated by broadband pump, and of course, the series of papers. And Girish Agarwal has been thinking about this back in the early days, also coming up with an interesting view, interesting theory of stimulated Raman scattering in chaotic fields as a part of this important early work. So as we think about the dynamics of statistical fields, it's no longer self-focusing as it is in this elementary view as it is shown here. It's not even laser filamentation in this view, self-focusing plus ultra-fast ionization as shown here in this simple animation. It's not even this bound state Soliton dynamics that we observe, and this is already where the beam becomes unstable because it develops those instabilities. It can be either t, can be either time here, or it can be a transverse coordinate across the beam. So because the picture, the whole physics is described by the same nonlinear Schrodinger equation. So this view of bound soliton dynamics becomes much more complicated. Right? The beam tends to break up into multiple filaments. So this is the result. This slide shows the results of our early supercomputer simulations done by Petr Zhokov, who was with me at Texas A&M University, and now he's continuing his computer work, working for OpenAI toward higher-end artificial intelligence technologies. So we calculated the beam dynamics without assuming, and supercomputations are necessary here because we are not assuming any symmetry on the beam, and the beam behaves as it pleases. Right? So it loses all the dynamics. It is seeded by random noise, and the structure that tends to show up in the beam is quite complicated, and of course it takes a lot of time and a lot of computational power to make those computations. Now we want to see whether, and of course, the equations that describe these dynamics are deterministic in their nature, right? We are talking about the nonlinear Schrodinger equation. So the question is, where do we have this interface between deterministic and stochastic in optical field instabilities? So let's think about a stochastic laser pulse or laser beam, doesn't matter. And we have some peak power, so we are looking at this peak power within the beam or across the pulse, but now it's a distribution. So now we can think in terms of the mean power, and we have the distribution. And we want to make sure that no self-focusing, no beam instability is happening. So we're below some threshold, say the critical power of self-focusing, which is usually the fundamental level of instabilities. So we need to calculate this area under the curve, and we want to be somewhere here. We want to make sure our mean power is low enough compared to this critical power of self-focusing to make sure this probability given by the integral is small. But this is for one pulse only. If we have more pulses, and then even more pulses, and then even more pulses, we have hundreds and thousands and millions of pulses, because we want to avoid this process over large samples of pulses. So now we want to think about the probability that the maximum of my peak power of this entire sample of pulses, its peak power is not higher than this critical power of self-focusing, right? So we're talking this probability of having no black swan event, right? On the stock market, I have this concept of black swans, something low probability but high damage, low probability but high damage phenomenon that tends to happen, and then everybody's ruined. So we want to avoid this black swan event here over large sequence of pulses, because if we don't, our optics will fail. Our optics will be broken, will be damaged. So we need to calculate this integral. Then we take 1 minus this integral, and we take power n of this, where n is a number of pulses in my sample, 1 million, 10 millions, depending on how long I want my optics to be there as a part of my high-power beamline. Now, an interesting thing is that regardless of the statistics, individual statistics that describes my distribution here, the distribution of my probability for my pulses, this limit for this value can only be found in only 3 classes, right? So there's no black swan probability, right? It gives me a convenient way to describe what I'm talking about. There's no black swan, once again. So this is my no black swan probability. I don't want this black swan to be there. So my no black swan probability in the limiting as the extreme limit, according to the Fisher-Tippett-Gnedenko theorem, can only be found in 3 classes. It's either Gumbel distribution, Fisher distribution, or Weber distribution. Only 3 distributions. So if it exists, if this limit exists, then it can only exist in those 3 classes of functions. And of course, the history is very interesting. Fisher and Tippett have published this paper in 1927, and then Gnedenko published this paper in 1943, and this entire theorem, this setting here has been formulated for this theorem. So those distributions are shown here: Weibulian distribution, Gumbelian distribution, Fisher distribution. Now, interestingly, Gumbel distribution is exponential of minus z, so it's exponential. The tail is exponential. It's a thin tail. Fisher distribution is different. It's a thick tail. It's non-exponential tail. This is where in my limit I have a thick tail, so my limiting distribution is weakly decaying. This gives me a very nice criterion of how to judge my rare events. This is where my rare events will be not that uncommon. This is where my rogue wave phenomena, this is why my black swans have to be expected. Now, in nonlinear optics, let me make this long story shorter. In nonlinear optics, I can find all three, right? And this is our contribution, the contribution of our group to the field, that this map of extreme events of statistics, extreme event statistics in optics, all three classes can be realized in optics, right? For example, in the class of polynomial nonlinearity, found through self-focusing, self-phase modulation, cross-phase modulation, harmonic generation, weak field harmonic generation, perturbative harmonic generation. Then multi-photon ionization, multi-photon absorption gives me polynomial nonlinearity. And this gives me very respectably behaving exponential of minus z Gumbellian distribution. Now, if I have exponential gain, which I find in spatial modulation instabilities, right, important to me because I want to avoid my beam instabilities, and also temporal modulation stabilities, the way my soliton tend to build up. Stimulated Raman scattering, or stimulated brilliant scattering, or laser gain, I have exponential gain. I will have the Fisher distribution. And then, of course, my statistics will always be transformed. My nonlinearity transforms statistics in some way. And this is here, I see my Pareto distribution. Pareto distribution has always been viewed as a suspect for rogue wave phenomena, right? Rogue wave phenomena, those rare event, extreme event phenomena, very damaging as ocean waves or any other phenomenon, other areas. They have been connected to Pareto statistics. But now we see the role of the Pareto statistics. It is this statistics of this nonlinear outcome, right? But then the limiting distribution found in the universal, in terms of the universal distribution, the Fisher distribution. So what we should really look at and use as a criterion is the Fisher distribution. And also Weibullin distribution can also be found. So in optics, we can find this. And for example, we can redefine the threshold of stochastic self-focusing. Right? Now, as we increase the number of pulses in our sample, right? Say if we want to design our beamline not for one pulse, not even for 1,000 pulses, but for 1 million pulses, we will have to work even lower, even further below this peak power threshold. How far below the peak power threshold we should be, this natural logarithm of n will tell me. Right? Because when the number of pulses becomes comparable with exponential of a squared over 2, where a is my simply signal to noise ratio. So I take my field and I find a way to quantify my signal to noise ratio. Sometimes this is not trivial, right? I'm looking at my pulses and I need to find a way to reasonably judge my signal to noise ratio. But then this is the only parameter I need to know. Then I'm safe as long as the number of my pulses in the sequence, right, is much less than this exponential of a squared over 2, right, where a is the signal to noise ratio. Now, what if I don't? What if I don't respect this? Now, this is what is going to happen. I will have those traces on my precious optics, right? And and also stochastic laser beams or stochastic laser pulses that nominally meet the deterministic beam stability criterion, meaning I'm working well below the critical power of self-focusing or the critical power or the peak power needed for the soliton to build up, right? The peak power of the fundamental soliton, right? So I'm working below every critical power, and yet, so I'm meeting my deterministic beam stability criterion, and yet, on a large pulse sample, my pulse of beam will emerge as unstable. It will emerge as unstable because this probability will accumulate, and depending on whether it's exponential gain or polynomial instability, I will have one dependence or the other, and I will end up with all those traces. Now, interestingly, the statistics of those traces is universally Poissonian, right? And this can be demonstrated demonstrated mathematically. So what do I mean specifically? What I mean specifically is that as long as my extreme value distribution, extreme value statistics exists in the sense of a limit of my distribution, right? If this limit exists, and it exists for polynomial nonlinearities, it exists for exponential nonlinearities, it almost always exists, as far as we're concerned, as far as the cases of practical interest are concerned. The number of exceedances, the number of times I'm exceeding my threshold will be Poissonian distributed. Right? It will always be Poissonian. The only difference, though, will be that my mean, the mean of my Poissonian distribution, the only parameter of my Poissonian distribution. Right? So this is my Poissonian distribution, and I have only one parameter, this tau. So this tau will be different depending on what the class of my nonlinearity is, whether it's polynomial, exponential, or some other nonlinearity, right? And I can describe it depending as a function of my parameters of my nonlinearity. Right, so this is a statistical part, right? And then, of course, those extreme events are everywhere. They're universal. In ocean physics, we're talking about rogue waves. In geosciences, we also talk about those rogue wave effects. Financial and insurance risk management, those, again, black swan phenomena. Biomedical diagnostics, extreme events in medical diagnostics, right? As a precursors, that's something that can help us respond to some rapidly growing conditions, and still giving us enough time, enough minutes to respond and to hopefully suppress some condition from building up. Natural disaster modeling. So how do we know? How do we even know that they exist, that this whole idea that extreme events is meaningful? Of course, we can try to ask black swans. They probably won't tell us much. We can decide to talk to ocean rogue waves, but they will kill everyone who dares to talk to them. Now, optics is safe, fast, and promising all around, but we need to develop the right language. We need to develop the right technology, and we need to learn how to ask the right question. And this is what we are trying to achieve. Now, the pioneering work in this direction has been done by Jalali and his group Optical Rogue Waves, and this Nature paper 2007, and then John Dudley, Jerry Gentil, and Ben Eggleton, and in this very nice paper and follow-up papers, again, John, Jerry, and Ben, they came up with the whole set of techniques and ideas of how to characterize these rare events in supercontinuum generation. Right? So by detecting those outliers in supercontinuum spectra, right? And nonlinear optics is very convenient in that sense. You have this highly nonlinear systems, such as highly nonlinear fibers, and you can see how those rare effects build up there. As a part of our work with Andres Baltushka and Ferenc Krauss some time ago, we worked toward this technology of Soliton self-frequency shift as a way to synchronize the pump and seed in the amplification scheme. So the characterization of Soliton instabilities is one possibility, is one of the possibilities here, right? And again, the Soliton shift and the supercontinuum generation. Supercontinuum generation can be viewed as a multiple solitons, giving me a much broader spectrum, and then covering broad spectral range. Now, as I was sitting next to Gustavo yesterday, I thought that Gustavo's nice work on stimulated brilliance scattering that he has done when he worked with Philip Russell, and then that which he's continuing now at Gleb Potagin Institute of Physics in Campinas. This is a very nice system, potentially, to study. So this, again, high-gain stimulated brilliance scattering is a nice system to look at extreme events scenarios, because stimulated brilliance scattering will give those enhanced extreme events outcomes. Now, at this point, as we're developing our understanding of the stochastic aspects, let me get back to the deterministic aspects and talk a little bit about the nonlinear Schrodinger equation. Right? Nonlinear Schrodinger equation is a framework that describes the evolution. Right? So we're still in this framework, our nonlinear beams or nonlinear pulses. If I have my beam, if I'm interested in beam dynamics, nonlinear beam dynamics, then this x is transverse coordinate. If I'm interested in the time evolution, then this x here will be my time, and then it will be time evolution. Right? And it's one-dimensional, again, the word of caution, of course, one-dimensional, because it's one-dimensional that makes system fully integrable. And fully integrable systems are wonderful, right? They have a respectable integral of motions, and the number of integrals of motion for the nonlinear Schrodinger equations is very respectable. It's infinite, right? So it has an infinite number of integrals of motion. And of course, there are different ways how you can look at nonlinear and the nonlinear Schrodinger equation. Now, one very instructive way of doing this is to use the inverse scattering method, inverse scattering transform. In fact, in application with respect to the Korteweg-de Vries equation, Korteweg-de Vries soliton, this inverse scattering problem has been around for a long time, since 1967. But as far as this nonlinear Schrodinger equation is concerned, it was Zakharov and Shabbat in 1972 who came up with this analytical solution based on the inverse scattering. And briefly, inverse scattering, instead of solving my nonlinear Schrodinger equation, I'm solving this equivalent scattering problem, right? Where my U gives me my potential. So this Q is U modulus squared, right? It will be my potential, and I consider scattering, this equivalent scattering problem. And then I'm solving the scattering problem. It's solved already, automatically solved. I know the solutions, and I can go back and forth. I can go back from my nonlinear Schrodinger equation from U to my inverse scattering problem through this transform. Technically, it's Gelfand-Levitan-Marchenko equation, but it's a transform. And it's very similar. I can recover my fundamental soliton. I can recover my more complicated solitons analytically. And it's interesting and instructive because it works, this whole idea of inverse scattering method, and inverse works in the same way as Fourier transform works for linear fields. For linear fields, we always know whenever there's linear dynamics, we always know that we're taking Fourier transform, and Fourier components will be behaving in a linear way as normal modes in a linear case. Now, if we have nonlinearity, then those modes are no longer normal modes. They will be coupled. And yet, we can somehow identify normal modes. But instead of doing linear Fourier transform, we're doing inverse scattering transform. So we're doing exactly this. We are transforming our nonlinear Schrodinger equation to the scattering problem. We're solving the scattering problem, and we're going back to the real space. Right? So this will be our nonlinear Fourier space, and this will be our real space. And then that's a full analogy. So we can identify, we can identify our normal modes. We can describe their evolution in time or along x. It's described, it's found, and then we can go back. And it works so well that we can come up with a legitimate quantization scheme. So we can continue it all the way to identify the correct quantum particles. Now, in the case, to put things in a perspective, in the case of a high nonlinearity, my inverse scattering transform ideally recovers the Bespalov-Talanov equation, this Bespalov-Talanov solution. Now, Bespalov-Talanov solution is problematic, right? Because of course it's a milestone in theory, but it assumes infinite energy, right? Infinite energy. And of course, simulations will show this, that for low nonlinearities, you're never achieving an agreement with Bespalov-Talanov theory. But in the case of a high nonlinearity, you have an agreement and you have a nice understanding as to why, as to how this agreement, how we can recover this Bespalov-Talanov result in terms of this waveguide analogy. So this entire picture becomes similar to the picture of linear modes in a waveguide. So we have this inverse scattering insights into field instabilities. Now I put this slide together for Wanderley, and then coming from this idea of inverse scattering transform, of course, I like very much this analogy between matter wave speckles and the decaying condensate. And it would be also interesting to look at some additional aspects from the viewpoints of not just speckles, not just linear objects, but nonlinear objects, such as laser filaments. So here, by filaments, I mean nonlinear objects, because filaments here, it helps me to describe a little bit more than a speckle. It's a speckle that is kept together by nonlinearity. So it's a manifestation of normal modes. Filaments are not normal modes themselves. The normal modes will be something different. Normal modes will be the action angle variables. But filaments will be the, I mean, like from my normal modes, I can come with these filaments. But this will be nonlinear objects. So the idea is that from this filamentation view, some interesting aspects of this already beautiful analogy could show up. But of course, beam instabilities, I need to think about. I need to think about ionization. This makes things more complicated. And over years, we have simulations that work very well. For example, in experiments that have been done by Andres Baltushka, and we were part of this work done in Vienna, showing how beams are evolving towards short pulses in a situation where we are many orders of magnitude above the critical power of self-focusing. Now, ionization makes things difficult, and this is what we observed in one of our recent experiments, published in 2022. We have one of those optical parametric amplifier, optical parametric oscillator system with this carrier envelope phase stabilization system based on supercontinuum generation in a hollow core-photonic crystal fiber. And as we're observing this supercontinuum generation in a hollow core-photonic crystal fiber, we observe this uncontrollable growth of noise here. And of course, they can be very insightfully understood in terms of ionization, because ionization is, it gives this dramatic growth in terms of the noise. So it's double factorial. So if you wonder if this 10 photon ionization needed to ionize, it's a nitrogen. So you need 10 photons to ionize it with a TiSat-Phi laser beam, TiSat-Phi laser pulse. So you have those orders and orders of magnitude in the increase of noise. So we will have to include this in the model. But ionization potential, of course, is a powerful source of noise and powerful source of instabilities. And having all those aspects, all those parts, all those aspects of scaling understood, we should be able to scale down those high-power laser experiments planned as a part of advanced beam laboratory facility experiments, for example, as a part of the RISE hub. So this is the scale of the experiment planned at Colorado State University. We are planning to scale it down to a tabletop experiment, and this is this table where this tabletop experiment will take place at Texas A&M. And as we speak, an honorable mention of my students who are making this experiment with the leadership of Zhenhuan Yi in the lab, Gita Matvey and Rajip working at Texas A&M. So extreme events in nonlinear optics. Again, we identified universal extreme value statistics. We know how to distinguish between exponentially tailed Gumbel distribution and exponentially and non-exponential tails in terms of the classes of nonlinearities. We know that sometimes, even when we nominally meet the criterion of beam stability, the beams and pulses can become unstable, can emerge as unstable on large pulse samples. We have this Poissonian property also as a universal property of extreme event statistics, and all those extreme event outcomes, such as laser damage in high-power beam lines, some very practical aspects. Inverse scattering transform helps to connect the dots, provides deeper insights into deterministic versus stochastic, recovers the Bespalov-Talanov results, serves to identify the normal modes of nonlinear wave instabilities, suggests the emergence of quantum field properties, and offers an alternative quantization of nonlinear fields, a path toward understanding quantum solitons. I'll quit at this point. Thank you very much.
Thank you, Alexei, for a stimulating talk. We have time for a few questions. Please, Wolfgang.
So the black swan phenomena comes out of the tails, you explained very clearly. Now, all these distributions, Gumbel and so forth, I have never heard of, but one I have heard is Levy flights. Levy flights are also relying on long tails, but you did not mention them here. Is there any connection, or is...
Yes. Levy flight will eventually end up in one of those classes. Fréchet distribution will be the candidate because it will be a thicker and heavier exponential tail. But it belongs to one of those classes, so it's universal.
So thank you very much for this very inspiring talk. So you mentioned about what would be the analog of the Fourier transformation for nonlinear optics. Can we use that to build like a Wigner function, the analog of a Wigner function, but now for nonlinear optics?
Yeah, the Wigner function would be an alternative way, and in certain ways, a better way, an illuminating way, to look into some aspects into how this entire universal extreme event statistics tends to build up. So I agree, this would be a great resource. So it's a part of it, a part of the story. I agree. Yeah.
More questions?
Thank you for the very nice talk. I thought regarding the rogue waves, nowadays their statistics were really well quantified by the satellite measurements. So I was a little bit surprised about your comment on the rogue waves, the ocean rogue waves.
Oh, we are talking about ocean rogue waves, right? Well, even about ocean rogue waves, this is not my area, ocean rogue waves, right? So I have to be careful here. But from what I see, it's once in a while we have one of those high-profile publications again arguing, oh no, this is not nonlinearity, this is a fully linear scenario where we just have the interference of multiple ripples all combining into something catastrophic, and then immediately there's a follow-up to that saying, oh no, that's still energy is being provided by a reservoir, this bath of energy, so there's still no direct consensus. But again, this is not exactly my field. What I'm more referring to, rogue wave as a way to describe some unwanted, low probability but highly damaging outcome in optics. And this is what we are looking at, and this is what we want to manage, this is what we want to be in control of as much as we can. But it turns out that we cannot control everything. Right? So I had it on one of the slides that most of the time it's not a question of if this is happening. The question is when this is going to happen. And this we know the answer to. this natural logarithm of n will give me the answer when exactly this happens.
You introduced a different type of quantization when you introduced the nonlinear Schrodinger equation. It's apparently different from the conventional definition of the quantization of optical modes. My question is, does it use the same zero-point fluctuation or the vacuum fluctuation?
Now, it is not guaranteed that this quantization will be the same. So these quantization procedures are different, and so this quantization, in fact, it has been spelled out here. I have it in an explicit form. I simply decided not to go into the details, but I will take this opportunity and will show this slide once again. So I'm identifying the normal modes, and I'm doing quantization in terms of the modes of a harmonic oscillator. So this is my P and Q, and they identified in terms of the action angle variables, just in the very canonical transformation way, right? The way according to the canonical quantization procedure. And it is different from the quantization leading to Bethe states. Bethe states, because Bethe states brings me to the localized states, but this is legitimate quantization. So it will be different. And then I can establish connection, but still my quanta will be different. My quanta, my particles emerging from this scheme will be linear combinations of these Bethe states. So eventually I should be able to reduce one result to the other. But originally, when those particles, the nature of those particles will be different, and so they will behave differently. Those will be solitons, they will be localized, either in space, in real space, or in time. And Bethe states are completely delocalized. And this is also a lot of quantization.
Okay, we have to move on, but I have to ask you a science fiction, what is perhaps a science fiction question. I'm always amazed by what creative material engineering can do. Now, we cannot engineer the ocean, but we can engineer our optics.
Absolutely, yes.
And do you think that there's any chance that above the damage threshold that you so nicely described, we can engineer the medium so that the light will enter a new realm of scattering or nonlinear behavior, which would actually suppress the damage and therefore kill the black swan as you described it?
So you're almost describing plasma, laser plasma, and then something relativistic, and then all of a sudden...
So, yes, self-suppression effect that comes above certain power.
Well, I cannot, of course, I cannot immediately come up with it. It will be difficult. I mean, as we're getting serious, it will be very challenging. So it will be more and more threshold as opposed to getting away from all the threshold. We will end up with more threshold and more limitations. But yeah, gas phase nonlinear optics.
Okay, let us thank Alexei. Thank you very much. Our next speaker is Wolfgang Schleich. I have to say that I personally learned a lot of physics from Wolfgang, so it's very nice to see you here. You want to stand here, or you can take a microphone. And Wolfgang is going to talk about Landau-Zener transitions, Hawking radiation, and number theory.
Well, first of all, I want to thank Vonley, of course, for giving me a chance to speak here in front of you and bring me for the first time to St. Carlos. I have made it often to Sao Paulo, but never to St. Carlos, and I really enjoy being here and having a chance to discuss with you. I've learned already a lot. It was very nice that Ron said that he has learned something from me. I learned a lot from me, he said even. But I have to say I even learned more from him because he did experiments that we had suggested. And in the course of these experiments, a lot of discussions took place. And as I said, I have learned a lot from you, Ron. Thank you very much. So Today, I'm going to talk and try to connect for you 3 different topics that on first sight might not have anything in common. Landau-Zener transitions, Hawking radiation, and number theory. I also want to draw attention to the fact that I'm coming from the University of Ulm. Marlon Scully once mentioned Ulm, ULM, University of Laser Measurements. And, well, thank you for laughing, because at that conference, nobody laughed. So here is an audience who knows where Ulm is. They also know that Albert Einstein was born, but he left when he was 12 months old. His parents moved to Munich, which is about 100 kilometers away. His parents started a company in electricity. They put the electric light onto the Oktoberfest in Munich. Most people probably don't know that. Now, I gave you away already where Ulm is. It's located between Munich and Stuttgart, halfway. There's a very fast train that connects you within an hour from Munich to Ulm. And I would like to see all of you in the future and come and visit us. You were already there, and many people in Wanderlei has visited us. So please, when you ever come to Europe, and before it's gone, come and see us. I also have a part-time position over here at Texas A&M University in the physics department as a Hegler Fellow. Like Wanderlei is also a Hegler Fellow. And so please come and visit us at Texas A&M. So, as I said, I will talk about the Landau-Zener transitions. This is a phenomenon that goes back to the 30s and requires heavy mathematics in order to understand it. You use special functions, the parabolic cylinder functions in the complex plane, and it needs Stokes lines and all this. And I want to show you that you can do the calculation and rederive the exact result. The Landau-Zener result is one of the very few exact results of quantum mechanics. And I want to show you a calculation, a one-line derivation of that result. Now, of course, you can say, oh, there's a lot of questions behind this derivation. Yes, and then we can discuss that in the session. Hawking radiation. What is Hawking radiation? It was mentioned yesterday in a talk already, and it's closely related to Unruh radiation. It's radiation, it's a quantum effect which is associated with the event horizon of a black hole. So it connects in some sense gravity with quantum mechanics in an elementary way. Now, when I say elementary, I don't mean simple way, but it's the simplest way you can connect the 2 theories. You don't need quantum gravity to do this. And I want to show you something that is at the very heart of this Hawking radiation, which you might have not seen before, and that is a logarithmic phase singularity. So the whole effect of Hawking radiation comes out of a logarithmic phase singularity. So you have a phase e to the I, you have a phase factor e to the I, and the phase itself goes like a logarithm of an argument. And the Fourier transform of such a function gives you immediately the Bose statistics that the Hawking radiation enjoys. And so I want to show you a very simple example where you don't need second quantization. You will see this effect too, which has also a logarithmic phase singularity, and that's the inverted harmonic oscillator. Ron yesterday mentioned in his talk, I don't know which one it was of the 5 talks he gave already, there was a talk yesterday afternoon in which he showed that he can phase space squeezing by sending the atoms against an inverted harmonic oscillator. And now I show you here that it's the same. We use an inverted harmonic oscillator to create a logarithmic phase singularity, and we will see something like Hawking radiation. This is not just talk, this is an experiment that was done by Gary Roseman at the Tel Aviv University, and I will show you for the first time we have measured the logarithmic phase singularity that is at the very heart of Hawking radiation. And as I said, this is related, very closely related, to the Landau-Zener transitions, because the exponentially small probability of a transition in Landau-Zener comes from such a singularity, a logarithmic singularity. And I will show you this too. I will then go to the number theory part, and you will see that there are similarities again. I will show you how you can factor numbers. We're not going to crack the codes or anything, but I will show you simple examples where you can use concepts from number theory to do factorization. And then at the end, of course, we're trying to win the $1 million prize for solving the Riemann hypothesis. And the Riemann hypothesis is, of course, a long-standing problem in number theory, but I will show you some insights that we have gotten into this problem. And of course, by no means have we solved the Riemann hypothesis, but as my friend John Neuberger always said, if we would just stay up till midnight, we would crack the problem. But of course, we never stay up till midnight. So let's get started. And you can read more about it in this work here in Journal of Physics B with my student Eric Glasbrenner, where we started from the well-known Hamiltonian here at the center, where the atom, a two-level atom, has, of course, two levels, but their levels are due to a time-dependent magnetic field, for example, going up or going down. These levels cross at time t equal to 0, and then, of course, the coupling between the two levels, denoted here by this constant g, will be most effective. Here you see Landau-Zener on the right, and an excerpt from historic paper, and here, of course, you see Lev Landau. By the way, Landau-Zener was a professor at Texas A&M, if you did not know that, during his career. Now, you can also read a lot in the work of Franco Nori. He has written several papers and reviews about this. But here is, in one line, the crucial formulation of the problem. So we start out with this Hamiltonian that I mentioned, time-dependent, explicitly time-dependent. And what we do is we transform away the diagonal parts, so that in the end, if I would integrate in the Schrodinger equation this term here, of course, that would give rise to a quadratic phase dependence, as indicated here. And of course, also this term will give rise to a quadratic phase factor, as indicated here. So we get rid of these terms by integrating them, and we now only couple straight the amplitude A for being in the upper state to the lower state by a time-dependent factor. And this factor varies with time quadratically. So if time is very large, either positive or negative, it varies very rapidly. And the same is true, of course, down here in B. Now we solve for a very simple initial condition. We say at time minus infinity, the atom is in the state A. And then we ask ourselves, what's the probability of finding at plus infinity the atom still in the state A? Now, for this initial condition, B at minus infinity would be 0. So we can integrate this equation formally in terms of A. So this would just an integral over this quadratic phase factor and A. And we substitute it into the equation for A dot, for B, and we will arrive at this equation. So you see this is, of course, an exact equation. The time rate of change of the probability amplitude A is coupled to itself, but it involves an integral from minus infinity to the time t. So this A, make no mistake, now depends on t prime. But it has also here a phase factor that varies very rapidly. And so you can imagine as you integrate this, and A would be slowly varying, nothing will survive from this contribution. Only when you get close to t equal to capital T, there will be a contribution. So when we see this in quantum optics with such an integral equation, what we do is we say, let's just forget about the complication. Just take the A out of the integral. This is sometimes called the Markov approximation. So we take the A out of the integral, and now, of course, even the professor can solve this equation because it says A dot is a time-dependent function times A. And so you have to integrate one more time. So you get a double integral of a quadratic phase factor with an integral that now also depends on this variable and another quadratic phase factor. So what you're going to get is an expression for, and as I said, this is the Markov approximation. Now that's why this A has an index m, because it is the Markov approximation. And so we integrate this equation and we get this double integral. But I have written this double integral already in a very simple way, namely that the integral really goes from minus infinity to t, where t is this integration variable of this first integral. But I can decompose this integral from minus infinity to 0 and from 0 to t. This is a quadratic dependence on t prime. As a function, this is a symmetric function. And the integral of a symmetric function is an antisymmetric function. And as a result, this is again a symmetric function. So this total integral here is vanishing. And you see there's no coupling between the two integrals. And these integrals are Fresnel integrals, which appear in classical optics everywhere. And so you know exactly what this integral is. It's, of course, a factor from square root of alpha. And then you get also pi over 2. And you see as a result, you're going to get this pi here, because it's a Fresnel integral. And it's an exponential because we have made a Markov approximation. And then you get g squared over alpha, which is, by the way, the exact result. So now you see in one line, well, some people said it's not one line, but because I explained it in a very slow way, it's a very simple derivation of an exact result making the Markov approximation. Now you might say, why can you make an approximation and still get the exact result? Well, it's really not an approximation because, as I explained already a little bit earlier here, oops, let me go back here. Oops, I'm going in the wrong direction. No. Backwards. This way. Yeah. Now I get it. Okay. So I explained already that these integrals here are oscillating very rapidly. And there's only a very small neighborhood when t is equal to 0 that there's a contribution. Now another derivation might be interesting, or before I go into this, let me show you a more detailed analysis is in this chapter 17 of a Brazilian birthday party for Victor Dodonov, which took place last year. A very nice meeting. And we wrote this in chapter 17, a different perspective on the Landau-Zener dynamics. And there you see a picture which really brings out the essence, in my opinion, of the Landau-Zener effect. There are 3 different domains, 3 different time scales involved of this Landau-Zener dynamics. The first one is when you start, and what I show here is the real part on this axis of the amplitude A and the imaginary part of the amplitude A. And you start out with the amplitude being 1. And then, of course, back here, we're going to be in the amplitude that is given by the exponential and the well-known result that was derived by Landau-Zener. And when you see now as a function of time, there are 2 radii here. This is the radius 1 in the complex plane, and this here is the radius given by the final end result of the Landau-Zener result. And the amplitude A follows for a long time the radius 1, long time, and then it deviates, and this is time t equal to 0. This is when the 2 levels cross. And then they go on, and then they oscillate around this trajectory that is given by the final result. These are what is called the Stückelberg oscillations here. So you see there's 3 different domains. The domain here where you follow essentially the radius 1, then the transition onto another radius, and then the Stückelberg oscillations, which finally lead you back to here. Now, in order to make the connection to the Riemann hypothesis, and in particular to the Hawking radiation, I want to show you something else. So here are another derivation, one-line derivation to this problem. And here are, again, the 2 coupled equations. A dot couples into B, B dot couples into A, and you have these quadratic equations, these quadratic phase factors. You can easily decompose these, decouple the 2 equations by just differentiating this equation one more time, and you arrive at this equation here. Now, usually this is when people get involved and bring in the parabolic cylinder functions. And then, of course, you lose all insight into it. So what we said is forget about the parabolic cylinder function, just forget about the second derivative here. Forget about the second derivative. Just take the A dot and the A, because this is like the equation I showed you before in the Markov approximation, where you had an AM dot is equal to something A, which is again an exponential solution. But now you have to be a little bit more careful, because you see the t, the argument on which A depends, vanishes at time t equal to 0, which means the highest derivative of this approximated differential equation becomes 0. So what we will do is we will introduce a little epsilon here to avoid this problem of the origin vanishing. So what we do is we divide this equation by I alpha t, so that we get an equation A dot is equal to AS with this factor here. And the epsilon, as I said, has been put in to avoid the singularity here at the origin. And what you find is if you multiply this expression with epsilon minus I alpha t, of course you get here like a Lorentzian, and if epsilon goes to 0, you notice this is the realization of a delta function, except the delta function is missing a factor of 2 pi, or 1 over 2 pi. Okay, so now that's where the factor is coming from. I'm sorry, it's a factor of pi, not 1 over 2 pi. It's a factor of pi, because of course the realization of the delta function has a 1 over pi in front, that which gives you the arctangent if you would integrate it. And the second part here, if you look carefully and let epsilon go to 0, is a term like 1 over t. 1 over t. And you still have to integrate this equation, and you get a logarithmic phase. So when you go back, the phase that I'm talking about is this particular angle here from the origin to the point on this circle. So as you move here, as time goes on, you have a logarithmic phase. And as t goes close to 0, of course, that logarithmic phase explodes. And that's where the transition comes from. But at the same time, of course, then you cannot neglect the second derivative. And so that's how you see the influence. But now keep in mind that that derivation shows you a logarithmic phase singularity. Now, with this, we stop and we go to this different topic of the Hawking radiation. Black holes have always been considered black. Why black? Because you cannot see the light coming back out. Light that goes in cannot come out. Now, Hawking proposed that, yes, there can be particles coming out because of a different mechanism. And he says, and this is the paper in Nature in '74, he says, from this follows that the number of particles emitted in this wave packet is given by this Planckian part here, times the number of particles that would have been absorbed from a similar wave packet incident into the black hole. This is the relation between absorption and emission cross-sections that one would expect from a body of the temperature in geometric units. So he says it's black hole, the radiation coming out is something like black body radiation. And he says it's photonic in nature because it has this Planckian spectrum. So some of you might notice that with Marlon Scully and Stephen Fulling, David Lead on Page, and in particular Anatoly Svizinski, we have worried a lot about different approaches towards the Hawking radiation. One of them was to look at an atom, a two-level atom, falling into a black hole and looking at the radiation or the excitation that in the atom due to the vacuum here. But you notice here's a mirror. Now you might ask yourself, why are we worried about a mirror here? We want to really define modes properly. So we are talking about modes that are defined here by that mirror. And these modes, all in a vacuum, interact with the atom. And what is remarkable is the expression for the probability of being in an excited state is given by the absolute value squared of an integral. So once you have worked through the mathematics, you arrive at this expression. Now, what is this expression? You notice here is the Fourier transform, e to the I x. Forget about this factor, it's just some factor here. And x is the integration variable. And you see x runs from 0 to infinity. And what you find here is e to the I nu times logarithm of x. So as x goes to 0, this expression oscillates more and more rapidly. And once you work this integral out, you're going to find this expression. And here is this factor that Hawking kept talking about, the Planckian spectrum. And of course, you're going to get several prefactors. So the key thing to remember here is really this expression where you have the Fourier transform of a logarithmic phase singularity. And as I mentioned to you, the same logarithmic phase singularity appears in the problem of Landau-Zener transitions. Now, but it also appears, I said, in a different system, and that is the inverted harmonic oscillator. So let me remind myself in your presence about the inverted harmonic oscillator. And here you see the potential, which is now going downwards rather than upwards. So here is the potential as a function of a one-dimensional variable x. And we have, in contrast to a normal oscillator, we have scattering states. So the first states that would be interesting is the domain of negative energy. So these would be states down here. And if the particle would come from the left, it would come in and would be reflected. If the particle would be above the barrier, so it would have been positive energy, then it would just pass the barrier, but it would slow down as it goes up the hill and then down the hill. So if you go to phase space, this would be now here P, and this would be X. Then if you would have a reflective trajectory, you would come in and be reflected. And of course, the momentum slows down, it gets small, and then it becomes large, as indicated by this particular trajectory here. If you're above the part, then you're here, and the trajectory would slow down, but again accelerate as you run down the hill. Now, there's a very peculiar trajectory, namely the one corresponding to the energy E equal to 0, the one that corresponds to the maximum of this particular potential. Namely, if you come here, the particle would stop, and stop at the top of the barrier. And this is this trajectory here, the so-called separatrix. It would stop here. And you notice that this diagonal in phase space, is kind of a barrier for the trajectories here, and the trajectories here, and the trajectory here. So particles cannot go into this domain unless they have started from the right. Of course, particles coming from the right could experience this part of phase space, but then they will not experience this part of the phase space. So in some sense, this area here is not accessible to the particles coming from the left, and this line could be viewed as a horizon. But this horizon now is not in position space, or I should say in space-time. This horizon is now in phase space. And it turns out that there's also a logarithmic phase singularity. If you follow this line all the way down to here, as you approach this phase space horizon, the phase of that state goes like a logarithm. Let me show you this. So if you look, so here is a paper I did together with Freya Ullinger and Matthias Zimmermann, I think like 2 years ago, and you look at the inverted harmonic oscillator, p squared minus x squared rather than p squared plus x squared, then you can introduce new variables like xi and pi, which are combinations out of x and pi. Now you might say, yeah, but we have that also in the normal harmonic oscillator. Well, in order to see the difference, in the normal oscillator you have x plus I p, and you have pi here, which would be like the creation operator. It would be pi or p plus I x. Now, where is the difference? Why is this I suddenly gone? The I is gone because in order to get this minus sign, the frequency of the oscillator has to be purely imaginary. So you have an I in the omega, and you see the omega that is down here had an I, and it canceled the I that you're familiar with from the normal harmonic oscillator. Now, in contrast to the normal oscillator, these operators are Hermitian. And if you rewrite the Hamiltonian in a different form, in variables of, or in operators of psi and pi, then you see that you're going to get something like psi times pi. And of course, you would say this is not Hermitian. Originally, of course, it is Hermitian, because it would be a symmetric combination of x and pi and x. But I have, on purpose, written it with the help of the commutation relation in a way that it would be psi and pi. And then, of course, due to the commutator, you're going to pick up an extra contribution. Now, if you would go to a representation of psi, then this would be just multiplication by psi. This would be differentiation with respect to psi. And if you would write the energy eigenfunctions given by this Hamiltonian, which is, of course, the same eigenfunctions of this Hamiltonian, but in different variables, then you will find that this wave function now has, as I said, a logarithmic phase singularity. So the energy wave function to a given energy E has an amplitude which goes like 1 over the square root of the variable psi. Why is it that? You can trace that square root dependence back to the commutator here. But what you can also see is easily, because of this function vanishing in front of the first derivative, you're going to get that logarithm. And remember, in the Landau-Zener, I told you, when you drop the second derivative, you have the first derivative, but the first derivative is multiplied by the argument time. And time vanishes at time t equal to 0. So that's exactly the same reason why you're picking up here a logarithmic phase singularity. So if you now would look in the Fourier transform of that particular function, so remember we have here the wave function, which is e to the I logarithm divided by the square root, and you take the Fourier transform, the one-sided Fourier transform, because you don't want to go over over xc equal to 0. If you do that, then you're going to get this result here. And you see this denominator now is not from a Bose distribution, but it's from a Fermi distribution. And now you might say, how did you end up with the Fermi distribution? I'm not talking about Fermi statistics, so please understand, we're talking just about ordinary quantum mechanics, no second quantization. The reason why this appears is because, in contrast to the Hawking radiation, our wave had that square root amplitude. So c equal to 0 has two singularities. It has the singularity due to the amplitude, and we have a singularity in the phase. Whereas in Hawking radiation, you have only one singularity, and that's in the phase, because the wave that you find is, of course, from the wave equation of electromagnetism. It is not from the wave equation, the Schrodinger equation. So now you see this. So now I want to just go to the experiment. Let me take you a few minutes through this. As I said, this is a paper that just came out a couple of months or two ago. A lot of credit has to go to Gary Roseman at Tel Aviv University, who did this experiment in the laboratory of Lev Schema and under the guidance of Adi Areh. As I said, we provided the theory with Freya Ullinger, Matthias Zimmermann, and Maxime. And what is the experiment? So the guys there, the guys there have a water tank that is about 15 meters in length. Now you might say, hey, you talked about quantum mechanics the whole time. You talked about the Schrodinger equation and so forth. Why are you suddenly getting involved in water waves? It turns out that if you have surface gravity water waves, the equation of motion for the surface gravity water waves is identical to the Schrodinger equation, with one small difference. Time and position are interchanged. Now that has a great advantage. You know how difficult it is to prepare quantum states. Somebody comes and says, I want this particular wave function as my initial state. It's very difficult to do this. How do you create in position space such a wave function? Now here with the water waves, it's very simple because the initial state is in time. So all you need to do is put your finger at the end of the water tank here and move it as a function of time in exactly the form that you want to create. So it's easy to create an airy wave packet. We heard yesterday about airy wave packets. And we have created airy wave packets in this water tank. And we looked at the propagation. Speaking of propagation, now this Schrodinger equation, as always, I have to tell this story because I still have a few minutes. When I was a student at the Max Planck Institute, the head of the theory group was Pierre Maistre. And he had a beautiful picture in his office of an old cowboy. And the cowboy had missed a couple of teeth and he wasn't shaven, he looked terrible. And underneath it says, there were a hell of a lot of things you haven't told me when I hired on. And in that sense, I haven't told you everything either, because this Schrodinger equation that I mentioned for water waves is not in the lab space. It is in a particular frame, and it is in the frame of the moving water. So as this wave that you have created here moves along, you have to measure the altitude and then transform everything back, so to speak, into the frame of the moving atom. So, but once you do this, you can measure the altitude or the excitement of this water wave, as I said, and it follows the Schrodinger equation. And so we can see now these phenomena that I showed you. Now the question is, how do you get into the Fourier transform? How do you get this variable psi in this experiment? Now in order to do this, we looked at something different. We looked at the free propagation. The free propagation is almost like a Fourier transform. And so what we did is we said, okay, let's create here a parabolic cylinder function, which is at the very heart of this particular problem of the horizon. Here at the beginning, and this is the theory plot. And then we let this parabolic cylinder function propagate along the canal. And you notice how it focuses, and back here, it really focuses into a way that you see only stuff here on this side, but you don't see anything on this side. So when you look at these curves here, you see hardly anything on the other side. There are certain approximations, but the real exact calculation is just having an amplitude here, but hardly anything here. Now here is the experiment below of Gary Roseman, and you see that indeed it reflects what you see here. And then we have analyzed the behavior along this line. You would call it the optical line. And here you see that the amplitude of the wave goes up and it becomes divergent, exactly like the square root behavior that I mentioned earlier. And here, what you see is the logarithm of the phase. And you see how it follows exactly the logarithmic phase singularity that we predicted. All of this comes out of measurements of these water waves, as you indicated here. These are typical measurements, and from this you can extract this particular information. So with this, I want to switch now to the last topic, the Riemann-Zeta function. Now you notice that there is a connection. The logarithmic phase singularity connects the Hawking radiation with the Landau-Zener transitions. Now how is this here with our friend Bernhard Riemann? Now this is the first page of a historic paper. It is the only paper that Riemann ever wrote on number theory. And it created the theory, the number theory. It really gave rise to this field. And I don't want to go through the whole thing, but you can read very clearly in German what he wrote. He said, I thank the Academy very much for inviting me to become a member. And this is the Berlin Academy of Sciences. They invited him to become a member, despite the fact that he was in Göttingen. And he said, what better to do than to write an article and send it to the proceedings of the Academy. And in those days, papers were not written in Tech and sent by email. They were written by hand. They were really, as the Latin word says, manuscript. So this was the original manuscript that Riemann sent to the publisher. And here is one equation that kind of motivated him to look at this problem. And when you go back here, the equation is here. This is the equation that I'm amplifying for you in the next transparency. And this part here at the beginning is the text where he talks about the Academy and going to a problem which even Gauss and Dirichlet and all the famous people would have interested. Now here, this equation is the following, and it connects a formula that was well known at the time of Riemann. On the right-hand side, there is a sum, and he doesn't even write what he sums over. He sums over all the natural numbers, 1, 2, 3, 4, 5, and so forth. And he has a complex argument, S, which has a real and an imaginary part. Now, on the left-hand side is a product. And also, he doesn't say what's on the product, but the product is, the members of the product are P, little p. These are all the prime numbers. And the S here is, of course, the same S. That's the complex argument, sigma plus I tau. So Euler was the person who established this identity, which connected a sum over 1 over n to the power s with all integers to a product in which only the prime numbers appeared. But this equation has a problem. It is only valid as long as the real part, sigma, is larger than 1. The minute you get to 1, or even smaller, this identity does not hold anymore. And Riemann's question was, how do I find the analytic extension of this function on the right-hand side, and can I find a similar relationship then that is valid in the whole complex plane, not just to the right of sigma equal to 1. Now, one thing that I noticed together with Connie Feiler some years back, and here I reproduce for you, again, a typical what is called Dirichlet sum. So here is a sum that goes over all integers, n equal n to the power s, and some expansion coefficients dn. And you might say, why would a guy in quantum physics be interested in this particular function? Well, very simple. Because if you take that function, this n here, and put it in an exponential form, then you see that the n appears in the logarithm, and you get a logarithmic phase here, but of course not a singularity, but a logarithm of that phase. So now you can ask yourself, hey, this phase factor almost looks like an energy spectrum, except that this oscillator does not have energy levels n plus a half, but it's the logarithm of n plus 1. So now how do I construct a potential whose energy eigenvalues are logarithm of n plus 1? And I don't want to go too deep into the details. Here is a potential that gives you exactly the energy levels that you want. It's almost like a harmonic oscillator. For small distances, it's a harmonic oscillator. For large distances, it goes like the logarithm of the variable. And so you can really find this particular potential. And this was together with Reinhold Walser, who is here in the audience. Many years ago, we did that. And so now you can ask yourself, can you factor numbers with this? Why would you think you could factor numbers? Because remember, the functional equation of a logarithm is that the logarithm of the product is the sum of the logarithms. So very simple, what you could do is have a two-dimensional problem or a one-dimensional problem with two atoms. And you give these atoms energy, logarithm of n times, or p times q. And then, of course, the atoms will be excited in this logarithmic potential. And in the end, the energy has to be distributed onto the 2 degrees of freedom. So one must have the logarithm of p, and the other one must have the logarithm of q. So you would immediately be able to do such a factorization scheme. You can also create potentials that have energy levels that are only prime numbers. Now I'm showing this, and we can even do this with BECs and the central potential. I don't want to go into it. Remarkable is that Donatella Cassetari and St. Andrews is doing experiments on realization of such potentials based on holographic schemes, and then you will see the nodes and can count from the glowing of the atoms, you know, the potential. So let me go to the very last part where we connected entanglement and analytic continuation. Why is that? I mentioned at the very beginning of this section that we have the Riemann-Zeta function, the Dirichlet sum. That particular sum here, the Dirichlet sum, is restricted in its convergence to sigma larger than 1. However, this line here, real part 1/2, is very interesting because Riemann claimed in his seminal paper that that's where lots of zeros are. As a matter of fact, all the so-called non-trivial zeros. Now, if you have a problem with convergence, you might say, let's just forget about the upper parts here and just truncate that sum at n and forget about the remaining parts. Well, it turns out that's a big mistake. If you keep the rest of these terms and rewrite them, you will get this expression here. And now you see here is the argument s, here's the argument 1 minus s, and you get something like a Schrodinger cat. So now if you go across the critical line, or the line 1, you will see that the zeta function is a superposition of two contributions. It's very similar to the Schrodinger equation, to the Schrodinger cats that, for example, Serge Haroche created in his cavity. So 1 minute, very, very small advertisement on the Riemann hypothesis. The lecture notes in physics celebrated its 1000th volume recently, 1,000 volumes, and we were asked to write a paper, and so I wrote a primer on the Riemann hypothesis with Michael Chaffon, Eva Taknova, and my friend Professor Helmut Meyer. I would never indulge in such a crazy field if I would not have the guidance of a professional. So Professor Meyer has had the chair of number theory at the University of Ulm, and he has had a very watchful eye on these activities. Now, what am I doing here? I want to use the concept of destructive interference to gain some insight into the zeros of this function. For this, we are looking at a function psi, which is not only zeta, but the gamma function, s minus 1, and an extra function. The beauty of this function psi is that now you have only zeros along the critical line. And you have a decomposition of this function into a new function f and a function f at 1 minus s. So you can construct that function by a superposition of a function evaluated at this point and at this point in the complex plane. Now, not only can you do this, but because this function f has a special symmetry, it's this point and this point which contributes in the end to finding xi. So you see it's a really wonderful symmetry. If you want to know the value of xi at this point, you have to take the function f at this point and add to it this function. And if this is a destructive interference, this function will have, xi will have a 0 here off the critical line. So all that matters is now you look at the function f, and here it is. Here is the function f as in its absolute value and its phase. And what you will find is something really surprising. Here is this critical line, and here are some of the zeros that I mentioned. These are the first zeros of the Riemann zeta function. And what you find is there's a phase line, a very specific phase line, pi over 2, and it wiggles around this curve constantly. And every time it crosses it, you get a 0 of the Riemann zeta function. And eventually it disappears, this line disappears in this 0. Now, in order to get destructive interference, you need a phase difference of pi between the 2 points. But you notice there is not even a phase difference of pi possible between the left here and the right, because this is the phase line pi over 2. So there's just no way. So there is a very drastic asymmetry in this function between the left to the critical line and to the right of the critical line. With this, I want to finish, and in the interest of discussion, I don't even repeat what I said. Thank you very much.
Thank you very much. Thank you. Okay, let's take a few questions, please.
So, very, very nice talk, Wolfgang. It's nice
Thank
to
you,
see
Randy.
you. So, part of what you talked about was something that seems to relate to deep water waves. This is the Benjamin Fear instability.
Oh, well, now you caught me on something. I have to admit, I don't know about that.
Is it the Schrodinger? Is it described by the Schrodinger equation with attractive interactions?
No. This is a linear Schrodinger equation. There's no nonlinearity in there, no attraction. So it is. We have also looked at water waves with the full nonlinearity. Mm-hmm. One would think that this nonlinear Schrodinger equation then would be very similar to the solitons, like Alexei talked about, but it's not. If you derive the water waves rigorously, mm-hmm. you will get an equation that is different from these equations that he had.
Okay.
So I hope I answered the question.
Yeah.
But
well,
we are here in the linear regime,
yeah.
and where you have just a normal linear Schrodinger equation.
Okay. With the nonlinearity, I think I agree with what you just said, the remark about describing bright solitons in a situation where the Schrodinger equation has a nonlinear term which
Correct.
is attractive.
Yes.
Okay.
So what we had done is we had looked at the Talbot pictures. So we did something like a Talbot experiment with the water waves and then increased the nonlinearity. And we could see how the Talbot carpet disappeared, but then we saw new structures that were not explainable with the help of a cubic nonlinearity. Because in the cubic linearity, there would be a symmetry, and that symmetry disappeared. Because in the nonlinear equation for water waves, there is this asymmetry. Yeah. Thank you, Randy.
Any other questions?
Yeah.
Спасибо, muito obrigada. Thank you for your talk. In fact, you mentioned Scully, and I visited one of his talks, and I was asking about Hawking radiation simulation with cold atoms.
Yes.
But my idea was to offer Bose-Einstein condensate to create this black hole horizon and so on. But that's just the idea, not to use water as a classical object, but to use condensate because it's macroscopically quantum. It's kind of cool. My question is, first, it's a very awesome talk, and the connection between Landau-Zener and Hawking and all the observations. Can you please repeat your interpretation of this behavior of zeta function from your perspective, from this quantum harmonic oscillator perspective?
Which function?
When zeta function, when you show the behavior, right? Like we have this spectrum when the argument more than 1 one and more than one, and then we have yeah,
yes. Now I see
because
what
you have the results, and then maybe you have your own interpretation.
So you mean this is here?
Yes, yes, and so you're offering your method with.
Okay, so, yeah, thank you for the question. So what happens is, what I said is, you're here, and it doesn't converge. So you would truncate that sum at capital N. Then you now have left a sum that goes from n plus 1 to infinity. And now what you do, from n to infinity, you take the Poisson summation formula, which gives you a sum of integrals. Then you can do the integral, and once you have done the integral, you arrive at this sum. Now you might say, and I think I see from your face now, that that's not your question. You said, why is there a Schrodinger cat? Here, you mean, why is there a gap?
Wolfgang, I apologize, and I apologize to you, but we're really running late, so you can
Okay.
take it up in the break.
Okay.
We have to conclude here, so let us all thank Wolfgang again. Thank you very much.